Okay, so over here we're going to be sort of doing a little lesson on transformations of functions. We're going to work with a bunch of parent functions, and then we are going to do one example of each type, um, work on how you can memorize each parent function, and then I have a packet of more practice problems that we can kind of work on after that. So any function can be transformed with the following transformations. Now, I kind of threw these plus and minus signs all over the place, but really they are not necessary. So more often than not, what you're going to see is that y, your output value, or your equation is equal to some function f of x. However, f can be transformed. So f of x is not quite enough. Usually we default to x minus h, okay? And then we also have plus k on the side, and out front we have a. Now I can go way into much more detail, but for right now, we're going to just focus on a, h, and k, and how they impact your function. This notation right here is using function notation. That would be assuming that your function could be modeled with something f of x. The x minus h really goes and swaps in wherever you have an x. The plus h or minus h, plus k or minus k on the side will go at the end of your function, and this over here multiplies by the main component of your function. So what does each piece of this do? So we have the a value, and it really matters if a is positive or negative. Its default is positive. Sorry, it's a little smudgy there. So when a is negative, it's going to change your graph, okay? So less than 0 means negative. A is a negative number. It affects the graph by reflecting it vertically or over the new, in quotes, x-axis. Because your x-axis might shift up and down as well because of the way I kind of show some tricks for graphing a little bit more efficiently. Then your minus h over here, oh boy, not the best marker choice. Your minus h over here is, oh, actually, before that one, jump to, let's do this blue. The a value itself, okay? Yeah, we looked at if it's positive or negative, but what about the a value itself? So when a is greater than 0, and this is ignoring the sign, okay? The sign was taken care of up there in the pink. If it's greater than 1, once you ignore the sign, it's a vertical stretch, so it does not impact your graph in the horizontal direction. It only affects your graph vertically. But then when the absolute value of a, again ignoring the sign, if a is between 0 and 1 or less than 1, it is a vertical compression. Some books will refer to this as a vertical shrink. Okay? Next was the h, right? If you have x minus h inside of this set of parentheses inside of your function, it will shift your graph to the right 8 units, h units. If you have x plus h, that also affects your graph by shifting it to the left. And the catch is that the x value needs to have a 1. So just ordered new highlighters. Don't worry, this is garbage today, I think. The catch is that the 1, the x needs to have a 1 in front of it. You can't have like a 2x plus something, 4x plus something. We don't look at it that way, okay? And last, I guess I can bust out the orange for this. We have plus k, and the k value is going to move your graph either up or down. So adding k, it's not quite backwards like the h's are. If it's plus, it's going to move it up, and if it's minus, it's going to move it down. Minus, you would think negative, but it moves to the right. Plus, you would think positive, but it moves to the left. So really, you just got to know what all these do. Now, I know I didn't highlight the y, f, or x, and hopefully when this is all said and done, you'll understand what their role is in this. Okay, so we're going to show you all of this by example. We're going to model it. And I'm not going to go as in detail as I would if, I was doing this with class, because the class would ask questions and we would have a lot of conversation. So I'm really just going to get kind of right to the point here. So this first equation over here is y, or f of x, is equal to x. This is the Okay, we have a few names that I can actually give it. One name is the identity function. If you didn't have that in your notes, might not be a bad idea to add that name in there. It's also the parent function. These are all parent functions when they're plain, no changes to them, but it's the parent linear function. Linear, obviously referring to the fact that it's a line. So f of x is equal to x. Next, when I go ahead and graph this line, I'm going to use purple right here, if you even just think of the relation or relationship between y equals x, right? Where is it on your plane that x and y are equal? Well, they're both 1 right here, both 2, both 3, 4, 5, 6, and so on. Everywhere that x is equal to y creates this line that cuts through quadrants 1 and quadrant 3. When you were younger and you graphed this using y equals mx plus b, you would have said y equals 1x plus 0, I suppose, and that would just be that you have a line with a slope of 1, a rise and run 1, and a y-intercept of 0. Now we're going to plot 3 points for these. The 3 points we're going to plot, I'm going to use pink and the purple. The purple I'm going to kind of refer to this point as my HK, my sort of central point. It might be a vertex, might be a point of inflection. In this case, it's not really either. It's just sort of the point I'm referring to when I do my transformations. And then this, I'm going to highlight in pink 2 points just to really show you what happens when you change up your graph of transformations and how it only impacts it vertically. So I think it's important that I point out those points. Obviously, every spot on this graph that's colored in purple is really a point. I just make some points bigger than others. So if I made up an example of a linear function using a, h, and k, it might look like something like, let's say, 9 over 2 parentheses x minus 4 minus 3. How do I know that this is a linear function? Well, x is only ever to the first power, so it's definitely linear. I'm going to move my equation to the right 4 and down 3. 1, 2, 3. There I am. That's the purple point right over there. From here, normally my slope is 1. But I have a vertical stretch of 9 over 2, which is 4.5. So instead of going up 1 over 1, I'm going to stretch my up by 9 over 2. So I'm going to go up 1, 2, 3, 4.5 over 1, and then down 1, 2, 3, 4.5, and 1. Some people might want to just go up 9, so it's 5, 6, 7, 8, 9, and over 2, which is also fine. It's not wrong. But if I'm showing what happened to those original pink points based on my transformation, it's important that we do our transformations correctly. The only reason a linear equation works out when you do more transformations, when you do different ways of handling that stretch or compression, is because it's composed of straight lines and there's not a lot of areas where things can get wild and crazy with that, okay? So here are my 2 examples. If I were asked to describe the transformations here, you might say something like a vertical, so you just kind of rattle off what's going on, stretch of 9 over 2. If the number is negative, you never include it in your stretch or compression. The negative is a reflection, comma, right? 4, comma, down, 3. So that's how you would describe your transformations, but let's just keep it moving. This all makes sense when we got a lot more examples going on. Y equals the absolute value of x. The name of this is the absolute value function. And what happens with the absolute value function is we are going to It's the absolute value of x, which is the function we just did. We're going to take the absolute value of that linear equation. When you take the absolute value, you really take any part of it that was negative, and we're going to make whatever that was negative into something positive. So what will that look like? So here I have a pipe cleaner, and this pipe cleaner is really showing me the absolute, this is showing me y equals x, the graph from above. Now, where is this negative? The y is negative when it's below the x-axis. So the part that's negative is between my fingers right now. That's negative. But if I take the absolute value of it, I'm going to fold it up because it becomes positive, all right? And you end up with this shape of a V, but that's only when we take the absolute value of x. Then when we do our transformations, you could have a vertical stretch, which means that these are stretched vertically and it makes it look more narrow. Okay, they're pulled up. Then we have where we could shift it to the right, left, up, or down. And we could also do a reflection. So if I just do a reflection of the x-axis right now, it would just look like that. So parent function, it's going to have similar to the last in the first quadrant. And it has a vertex right there at HK. And then it's going to go up and over in the second quadrant. And then the points that we're going to focus on for my stretches or compressions are those right over there. So if I make up an example, let's do -3 absolute value. That's how you know it's absolute value function. It'll have absolute value. X plus 7 plus 4. All right, I know it's absolute value because it has absolute value bars in it. So I'm going to move my absolute value to the left 7, then up 4, plot my vertex. The negative is my vertical reflection. So now it's opening downward, so it's going to be something like that right there. And then the 3 is my stretch, my vertical stretch. It's going to impact the, if you want to call it the slope of each side, I guess you could call it that. So you could just go, instead of out 1, down 1, we're going to go out 1, down 3. Out 1, down 3. Out 1, down 3 again, and again. Now the points that are my pink points, essentially, are these two right over here. That's what happened to my original 2 pink points. Just going to connect these right there. And that's what you got. Absolute value function. That's it. You met it. So this is going to have a vertical. Stop spelling vertical with C-L-E. Okay, vertical. Vertical reflection. Vertical stretch of 3. Then left 7, up 4. Those are your transformations. Next, this one is called quadratic function. The name of the graph is actually called a parabola. What does that graph look like? There's been many talks in class about this, but quadratic, or the squaring function, is created by squares. Now, if I plug in 1, I get 1. If I plugged in 2, I would get 4. If I plug in 3, I would get 9. The cool thing about the parabola is once you know where the vertex is, you're going to go out 1, up 1. Out 1, up 3, and out 1, up 5. And that's because all the perfect squares, if you keep listing all your perfect squares, square of 0, 1, 2, 3, and so on, are separated by increments of the odds, consecutive odd increments. It just helps you sketch the shape of your graph. So if I make up a transformed version, negative 1/2 x plus 5 squared plus 6. How do I know it's a parabola? Because of that squared right over there. Take it from there. I'm going to go left 5, up 6. That's my vertex. Now from there, the negative is going to reflect my graph vertically and be 1/2 is going to be a vertical compression by 1/2. So if my normal pattern would be to go 1, 3, 5, and 7 vertically, instead I'm going to go 1/2 of each of those values. Out 1, down 1/2. 1/2 of 1 is 1/2. Out 1, down 1 1/2. Out 1, down 2 1/2, which is 1/2 of 5. Out 1, I'm going to go 1/2 of 7, which is 3 1/2. Trying to give you a little time to think, so hopefully kind of got the hang of it. Could go a little bit more, I have room. So next is 1/2 of 9, which will be 4 1/2. That's 3, 4 1/2. Now 1, down 1, 2, 3, 4 1/2. And then kind of run out of room. And then you connect it as best you can. And there we go. Best parabola you ever made. So what are we going to say? We got a vertical reflection, vertical compression, by 1/2 and left 5 up 6. There you go. That's all of it. All right, next up we have x to the 3rd power, and this has a simple name as well. It is called the cubing function. All right, so what is the cubing function? What does that graph look like? Well, there's not a fun pattern that's super easy to remember like there is for parabola, for quadratic. The cubing function is just, plug in 0, you get 0. Plug in 1, you get 1. Plug in 2, you'll get 8. So you could remember over 1 up 1 and over 1 up 7. But then when you plug in negatives, if I go left 1, I'm going to get negative 1. If you plugged in negative 2, you would get negative 8. So then you would go over 1 down 1, over 1 down 7. So that graph is going to look more like this. It shouldn't curl back over itself. Okay? And there you go. You have your parent function of the cubing function. And from here, I'm going to apply a compression on this. So I'm going to do a compression of, I guess, a half. Not too creative, but 1/2 parentheses x minus 1 to the 3rd plus 1. All right, that's my equation. Where's my graph moving? Well, I'm going to go to the right one and I'm going to go up 1. So my point of inflection, this is really a point of inflection, but HK, if you call it a vertex for now, I won't be too mad. And then we have a compression. So instead of going over 1, up 1, over 1, up 7, like the original, I'm going to go over 1, up half of 1, so a half. Over 1, up half of 7, so 3 1/2. Over 1, down half of 1, which is 1/2. Over 1, down half of 7, which is 3 1/2. Now, maybe I can fit another number here. What would the other number be? Well, next would be from, you go perfect cubes, ready? Your perfect cubes are 0 cubed is 0, then 1 cubed is 1, 2 cubed is 8, and 3 cubed is 27. So that's 1 unit, 7 units. How far are 8 and 27? If I go up 10, 20, I'd be at 28. So I'm going to go up 19. Half of 19 is going to be 9 1/2. And I'm not really going to fit that on here, but, you know, next time maybe you will. Then we go ahead and draw a graph. And pretty good. Again, what are my pink points when they were transformed? They're right over here. 1 and 2. And the big purple dot is my HK, or in this case, it's my point of inflection, which is where your concavity switches. So I go from being concave down to concave up. The scoop, the shape changes in that way. It's called concavity. Now on this page, we're going to have the two, sort of like an arch nemesis equation. The arch nemesis of x squared. That's the square root function. Now, what will that look like? It's very similar to the square, the x squared, the quadratic. If you plug in 0, you'll get 0. I'm going to go up 1 over 1 because if I plug in 1 for x, I get 1 out of it. Then I'm going to go up 1, but over 3. Now I'm at 4. If I plug in 4, I will get out 2. Up 1 over 5. And what it ends up looking like is the top half of a sideways parabola. So something I remember when I write x under a square root, I try to remember, like, pretend the shape of the square root symbol is like that shape of the graph. Kind of help me remember. And that also reminds me that you're going sideways with your pattern. 1, 3, 5, 7. And there's my 1, 1. And that could be a little bigger. Do not put an arrow at the end of this, okay? It does not have an arrow. So next, a transformed version of this. Let's do negative 4 square root of x plus 9 plus 8. Okay. I'm going to go left 9. I'm going to go up 8. Puts my starting point right over there. Now normally the negative just reflected me over, so I would go down 1 over 1, down 1 over 3, down 1 over 5, and so on. But it's a negative 4, so there's also a stretch. So down 4 over 1, down 4 over 1, 2, 3, down 4 over 2, 4, 5, down 4, 1, 2, 3, 4 over 7, 3, 4, 5, 6, 7. Plenty of graph. And now I'm just going to go over here. And it should feel pretty natural to draw the curve in there. Nothing should jump out and be kind of funny feeling. Usually if I feel something feels off and funny when I'm graphing, it's because I plotted a point correctly. Okay, next up, the arch nemesis of x cubed, the cube root. It's going to be very similar. It's going to be sideways also. However, it's going to give us the, the full graph. It's not going to cut off part of it. Down 1 over 1 and down 1 over 7. Here's the thing. I even just did it. I was about to tell you guys not to, and then I just did it. you don't go to 7, you move over 7 from 1, and that's what gets you at the 8, okay? So don't mess up how far you're moving, okay? Alrighty, there it goes. And from here, those are my 3 points. And the purple one right here. Alright, so what if I had 5 cube root, you always make sure that little 3 is in that hook real nice, of x plus 2 plus 1. That's going to move me left 2, up 1, up 5, 1, 2, 3, 4, 5, over 1, up 5, over 1, 2, 3, down 5, 3, 4, 5, over 1, down 5, 1, 2, 5, over 3. Oh, I didn't mean 3. I lied. It's supposed to be 7. So that 3 over should be 4 more. 5, 4, 5, 6, 7. And that 3 should be 4 more. 1, 2, 3, 4. Should be 7. My mistake. I started thinking of a square root instead of a cube root. So even though these are a little more extreme, you should still be able to draw a curve fairly accurately if you take your time. And my 2 pink points are going to be these 2 right here. That's it. And we have really one more to talk about today. The other one we're going to talk about, 1 over x. I guess I could do one more of this. We'll see. This is called the reciprocal function. Now, things that you have to remember about the reciprocal function are that we are not allowed to get 0 in my denominator. If you're not allowed to get 0 in your denominator, that means x absolutely cannot equal 0 since x is the only thing in my denominator. So going down here, I'm going to draw in that vertical asymptote we talked about at the beginning of the year. Okay, next, I also, as x gets bigger, if I plug in 1, I'm going to get 1. If I plug in 2, I'm going to get a half, a third, a fourth, a fifth, 1/10. So this branch is just going to get closer and closer and closer and closer to the x-axis as it gets bigger. And if I plug in a half, I'm going to get 2. If I plug in a third, I'm going to get 3. Fourth, I'll get 4, and so on. So that branch will keep getting closer and closer that way. Here, same idea is happening. So what do? We're having the same approach feeling happen. So what does that tell me is that this over here will be my horizontal asymptote. So when I transform this graph and move it all around, everything else is just going to go with it. So let's make up an example. What if we had negative 3 over x plus 4 minus 2? That is the transformation of that. I'm sorry. Left 4, 1, 2, 3, 4, down 2. So right here where I put this little plus sign, that's sort of like a crosshair of where my 2 asymptotes are going to intersect one another. So if I go over here, I'm just going to draw my horizontal asymptote right there at y equals negative 2. And I have a vertical asymptote right over here at x equals negative 4. The negative took the 2 points that would normally be here, move there, and there, we should move there. And now we have those 2 points, but then it's a 3. So not only is it 1 unit away, it's now 3 units away. 1 becomes 1, 2, 3. Now, really, you could plot more points if you wanted to. Definitely don't need to. If I filled in negative 1, there's this type of symmetry that's going on. But it's okay, we don't have to worry about it. There we have it. Last one. I call this graph, you know I'm not alone, a volcano, because it looks like a volcano. And the volcano is 1 over x squared. So over here, I'm still going to have the same asymptotes. But being that I have a square on the bottom, I'm going to kind of have that same behavior, like up and up and down, that'll kind of like influence this graph here. If I plug in 1 squared, 1 over 1 squared, I still get the 1 and the 1. And then my branches still get closer and closer. But obviously we could pick numbers that are a little bit taken out and about and kind of get a more clear graph. Oh, I didn't even explain this. So if I plug in -1, I'll get -1 squared is 1, you'll get +1. So that's why we call it the volcano. If you look at the look of it, it looks like a bit of a volcano. So what if I had 4 over x plus 2 squared plus 3. Left 2, up 3. That's going to be where my asymptotes meet. My vertical and horizontal are all done. It's not negative, so it's still up here. It's normally 1, 1, but there's a 4, so 1, 2, 3, 4 instead. Same idea right here. Some functions, not the way it's in the shape that it's in right now, being transformed, but you're going to learn about functions being odd or even. Odd functions are going to be symmetrical this way, so this is odd. Even functions will be symmetrical in this way, so this is even. So maybe I'll go through with another colored pen. Ooh, and I should put those pink dots on. That just reminded me. So here's my pink of these two, and then here. So make sure I got everything. Yeah, so from the top, I'm just going to go through them with a different pen, and I'm just going to mark them all as even or odd, and we will expand on that later. Just the parent function, not the transformed one. So this is an odd function. This is even underneath it. Next. This over here is even. This over here is odd. This over here is neither. This over here is odd. What did we say this was before? This is odd.